Okay, so this problem is an example of a torque balance problem. It's Anita and Oren, which are two paramedics, rush a 60-kilogram man from a scene of an accident to a waiting ambulance carrying him on a uniform 3-kilogram stretcher held at the ends. The stretcher is 2.6 meters long and the man's center of mass is 1 meter from Anita. How much force must Oren and Anita each exert to keep the man horizontal? So I'm going to move this out of the way. The solution to these problems for torque really comes from drawing a decent picture. Decent meaning big enough to represent all the forces that you have going on. So I have Anita and Oren, which are standing at the ends, presumably lifting up. So I'm going to assign Oren on this side, and I'll say Anita is on this side, holding up a man which is laying on the stretcher, something like this, where his center of mass is 1 meter in from Anita. So if the entire thing is 2.6, 1 meter is probably right about here, acting down from his weight, F of G. F of G is mass times gravity, so in this particular case it is 60 kilograms times 9.8, which is 588 newtons. Additionally, the actual stretcher has mass, which is 3 kilograms. A uniform object is always measured from the middle, so we're going to assign an F of G here in the middle as 3 times 9.8, which is 29.4 newtons. All right, so if I'm going ahead and move this out of the way so that we can see this picture a little bit clearer. If the stretcher, it has a total length of 2.6 meters, then we know that this is in the middle at 1.3 meters from either side, and we also know that from here to there is 1 meter. All right, so when it comes to the torque balance problems, the entire function is to set the net torques as vectors equal to 0. And in order to do that, you have to identify a pivot point. The pivot point can be placed anywhere in the problem to create balance, but the best thing to do is to place a pivot point at one of the unknowns. Doing this makes the torque bar 0 for Oren, which means that the force for Oren can't be calculated, but it also isn't affected in the problem. By putting the fulcrum at Oren, we take out his torque, and we also are able to then identify all of the torque bars for each individual force. So for example, for the stretcher itself, this is now the radius of the stretcher, which is half the length of the stretcher itself, which is 1.3 meters. But that also allows us to take the torque arm for the guy, which, since he is 1 meter in from Anita, that makes the radius of the man 1.6 meters. And then, of course, from Oren all the way across to where Anita is 2.6 meters, which is the radius of Anita. Now, this is assigned by us and could have been other ways around, but this is the most straightforward way of thinking of it, in my opinion. Once you have all of the torque arms labeled, then the key is to just note where these torques would be and how that would affect the system. So, for example, the stretcher pulls down, which as a torque is going to pull clockwise. The man pulls down, which as a torque is going to pull clockwise. And then Anita, who pulls up, if the pivot is here, is going to cause the system to rotate counterclockwise. Right? So taking the frame of reference rotationally as clockwise is positive, then using the net torque formula as vectors, we can say that the torque of the stretcher plus the torque of the man minus the torque from Anita must equal 0 for the system to balance. From here, it's a matter of substituting in all the various forces and radii that we've already labeled. Once you've solved for the force of Anita as 377 newtons, one solution to find the force of Orrin is to reverse the process. In other words, move the pivot point to where Anita is and repeat. So if I were to think about the stretcher again, I'll just redraw it so that we can see it. I know that Anita is now pulling up at 377 newtons. I know the stretcher is pulling down at 29.4 newtons, and I know the man is pulling down with a force of 588 newtons. Orrin is out here on the left-hand side and is the new unknown. One way, as I mentioned, is to just put the pivot point over here and repeat the torque analysis. If you do that, you need to make sure that you pay attention that the distance for the man as the radial arm is no longer 1.6. It's just this 1 meter distance that was originally identified. However, there is a simpler way. This system is not only balanced rotationally, but it's also balanced laterally, vertically. So if we think about the fact that up is positive as a frame of reference now, instead of worrying about the rotation, then the forces that act up are balancing the forces that act down, and the system is not accelerating. It's not moving up or down. Therefore, the summation of the forces in the vertical direction are equal to 0. And so we've got force of Anita plus the force of Orrin minus the force of the stretcher minus the force of the man equals 0. And so in this particular case, the force of Orrin is the force of Anita minus the force of the man and the stretcher.